In this video, I want to bring together a range of ideas and techniques that lead to an ordered and systematic checklist for sketching a curve in the plane. Of central importance are the sign diagrams for the first and second derivatives. The sign diagram of the first derivative tells us where the curve is increasing or decreasing and where turning points or local maxima or minima occur. While the sign diagram for the second derivative tells us where the curve is concave up or down or inflected. Let me begin with discussing what it means for a function to be increasing or decreasing. I will provide some contrasting examples and relate these ideas to the sign of the derivative. That is, whether the derivative is positive or negative over a given interval. We say that a function f given by the rule y equals f of x is increasing if the outputs y gets bigger as the inputs x get bigger. By getting bigger, we mean moving in the positive direction, to the right along the x-axis and upward along the y-axis. The simplest example would be the function y equals x, whose curve is a straight line sloping upwards. Naturally, as x gets bigger, y equal to x also gets bigger. A more precise definition involves the less than relation. If a and b are two numbers, and a is less than b, then b is bigger than a. Thus, y equals f of x is the rule for an increasing function if a less than b implies f of a less than f of b for inputs a and b. This makes precise the idea that as x gets bigger, going from a to b, then f of x also gets bigger, going from f of a to f of b. Often, the contexts in which the rule of the function is being used restricts the inputs. Typically, a and b will come from some interval on the real line that is of particular relevance for a given problem. This will become important later when we interpret sign diagrams and sketch curves. We say that a function f given by the rule y equals f of x is decreasing if the outputs y gets smaller as input x gets bigger. A simple example would be the function y equals minus x, whose curve is a straight line sloping downward. As x gets bigger in the sense of moving in the positive direction, y equal to minus x gets smaller in the sense of moving in the negative direction. More precisely, y equals f of x is the rule for a decreasing function if a less than b implies f of a is greater than f of b for inputs a and b. Note how the inequality less than for inputs turn around into greater than for outputs. Functions whose graphs are lines fall into three classes. They are increasing if the slope of the line is positive, decreasing if the slope is negative, or neither increasing nor decreasing if the slope is zero. That is, if the function is constant. Consider the simplest quadratic, y equals x squared, whose graph is a parabola with lowest point at the origin. The function is increasing if inputs are restricted to being greater than or equal to zero, but decreasing if inputs are restricted to being less than or equal to zero. If inputs are allowed to be taken from anywhere on the real line, then the function is neither increasing nor decreasing. Consider the simplest cubic function, y equals x cubed. Whose graph looks like this with an inflection at the origin where the tangent line passes through this curve. This function is increasing on all of the real line, even though it seems flattened out momentarily at the origin. It's always the case that if a is less than b, then a cubed is less than b cubed. Here are the graphs, the natural logarithm and the exponential function on the same diagram. They form a natural pair of increasing functions obtained from each other by reflecting in the line y equals x. The exponential function is increasing on all of the real line without any restriction on inputs. The natural logarithm function, however, is increasing over the positive reals. Remember, you aren't allowed to take the logarithm of zero or of a negative number. The fact that both are increasing on their respective domains is not an accident. It's a nice fact, elaborated on a bit later, that if f is increasing, then the inverse function f to the -1 is also increasing. The function associated with exponential decay, y equals e to the -x, is by contrast decreasing on all of the real line. This is to be expected because it's the result of reflecting the graph of the increasing function y equals e to the x in the y-axis. Reflecting graphs in the y-axis interchanges increasing and decreasing functions. The circular functions y equals sine x and y equals cos x undulate forever backwards and forwards. So they are neither increasing nor decreasing over the real line. If we restrict the domain of the sine curve to the interval from minus pi over 2 to pi over 2, we get a fragment of the curve which now represents an increasing function. This is the standard restriction that is used to invert the sine function. If we restrict the domain of the cosine curve to the integral from 0 to pi, we get a fragment of the curve which now represents a decreasing function. This is the standard restriction used to invert the cosine function. It's a general fact that increasing and decreasing functions are invertible because they satisfy the horizontal line test. And these restrictions of the sine and cosine functions are two such examples. The natural exponential and logarithm functions are also examples that we've come across earlier. It's a general fact that the inverse of an increasing function is increasing, and the inverse of a decreasing function is decreasing. You can see how this works geometrically with these restrictions of sine and cosine. For example, take the restriction of the sine curve, which is increasing, and the line y equals x. And when you reflect it, you produce the inverse sine function, which is also increasing. If you take the restriction of the cosine curve, which is decreasing, and the line equals x, and we make a bit more room in the vertical direction and reflect it, you produce the inverse cosine function, which is also decreasing. Here's the graph of the tan function, which is neither increasing nor decreasing over its entire domain. Though it's comprised of these infinitely repeating pieces sandwiched between and separated by vertical asymptotes, and each of these pieces represent an increasing function. Let's highlight one of them. The result of restricting the tan function to the interval strictly between negative pi over 2 and pi over 2. This is the standard restriction to make the tan function invertible, and the result is an increasing function. Here is the graph of the inverse tan function, which is also increasing. What about a physical example drawn from real life? Here is a curve that describes the distance function of a car trip from Skeldon to Georgetown. While it's generally sloped upward as you move from left to right, there are two places where the curve is flat, corresponding to rest periods in the trip where the car isn't moving. But there are many intervals of time on that trip when the car is moving all the time, such as this section from Abari to Maikoni. And over that time period, the function is increasing. If you're inside a car, but not looking outside, you could be sure that the car is actually moving because you could always see a positive velocity on the speedometer. Even though it might be fluctuating from moment to moment. These positive velocities correspond to slopes of tangent lines to the curve, which are derivatives of the function. It's clear then that if all the derivatives are positive, then the car is moving at positive velocities, moving closer to Marconi from a barrier, which just means in our mathematics parlance that the associated function is increasing. This is a physical demonstration of the following mathematical fact. If the derivative is positive on an interval, then the function is increasing. We have correspondingly that if the derivative is negative on an interval, then the function is decreasing. You can think of this physically in terms of a car moving backwards in the reverse direction with negative velocities. Consider a function with rule f of x equals x cubed minus s. Then the derivative is 3x minus 1. Sorry, 3x squared minus 1. Observe that if 3x squared is greater than 1, then the derivative is positive. This occurs when x squared is greater than a third, which is precisely when x is greater than 1 over the square root of 3, or less than negative 1 over the square root of 3. Thus, the curve for this rule will be increasing on the interval from 1 over root 3 to infinity, and from negative infinity to negative 1 over root 3. Observe also that if 3x squared is less than 1, then the derivative is negative. And this occurs when x lies between negative and positive 1 over root 3. Thus, the curve will be decreasing over this interval. Notice that the rule of f factorizes as x times x plus 1 times x minus 1. We're also aware of the importance of plus or minus 1 over root 3. So here's the curve crossing the x-axis at these points, as we noted before. Increasing for x less than negative 1 over root 3, and for x greater than 1 over root 3, and decreasing for x in between. What we've just completed, in fact, are some of the main steps in the technique of curve sketching. Notice the importance of the sign of the derivative, whether it's positive or negative. and that can be captured in something called a Sine diagram for the derivative in the form of a table, where there's a horizontal line that represents the real line. And we note the important points, plus and minus 1, over root 3, where the derivative is 0, and the changing sides of the derivative from positive to negative to positive, which correspond to the curve being increasing, decreasing, and then increasing again. So far, we have discussed what it means for a function to be increasing or decreasing, and saw a few familiar examples interpreted with this new terminology. And we noted that if the derivative is positive on an interval, then the function is increasing. But if the derivative is negative, then the function is decreasing. This is a good point to transition into a more general discussion about sine diagrams and look at some examples of how they clarify and inform our understanding of graphs of functions. A sine diagram is a special type of table with two rows. The first row for indicating values of a variable, say x, and the second row for some expression involving the variable. Let's take the example, x squared minus x, which we can factorize to be x into x minus 1. The line separating the rows is a copy of the real line. On that line, we indicate important points relevant to the behavior of the expression, such as when it becomes 0 or undefined. For example, x squared minus x becomes 0 if x equals 0 and 1. So we mark off 2 points on the line and label them with 0 and 1. Below this line, we indicate the way the expression behaves with a 0 or undefined at the indicated points, and whether positive or negative between these points and on either side to the right or to the left. So for this particular expression, the value is positive for x less than 0 or greater than 1, and negative only for x between 0 and 1. Later, I will give an example with an expression where at a particular point, the expression is undefined. This completes the sine diagram. This particular expression is a quadratic. So the associated curve is a parabola. It's bowl-shaped up because the coefficient of x squared is positive, and passing through the x-axis at 0 and 1. The parabola sits above the x-axis for x less than 0 and x greater than 1, corresponding to the plus signs in the sine diagram, and below the x-axis for x between 0 and 1, corresponding to the minus sign in the sine diagram. The sign of the derivative gives us information about where a function might be increasing or decreasing. So let's investigate the derivative of y. which we will denote by y dash. In this case, the derivative is 2x minus 1. Observe that this derivative is 0 precisely when x equals half. So we can draw a sine diagram marking off the point x equals half. And we can put a 0 directly beneath. And then plus to the right, where 2x minus 1 will be positive, and minus to the left, where it will be negative. The signs tell us that the curve is increasing for x greater than a half, and decreasing for x less than a half. Both of these match exactly what we see on the curve. This also confirms that the point with coordinates half and negative a quarter is the lowest point on the parabola. We can informally draw a small line sloping downwards beneath any minus sign to indicate decreasing, and informally a line sloping upwards beneath any plus sign to indicate increasing. Now, what about the second derivative? Sorry, the second derivative of 2x minus 1 is just the constant 2. And the sine diagram is very simple. There are no x values where the second derivative is 0 or undefined. The second derivative is positive everywhere, indicated by a plus sign. We can have an informal notation, which is a bowl-shaped up symbol, which has a technical term, concave up. When we see a plus sign for the second derivative, then we know the curve has some kind of bowl-shaped up behavior over the relevant interval. We'll say more about the technical meaning of concavity in a later video. In the case of this parabola, you can imagine the tangent to the curve as you pass from left to right, having increasing slope in the sense of becoming more and more positive as you move from left to right. This is exactly what the sine diagram for the second derivative is telling us, causing the curve, to have the shape of a bowl facing upwards. This upright parabola is concave up. But if we tipped it over, it will become what we call concave down. Then there will be a negative sign instead of a plus sign, and an inverted bowl shape down or sad face symbol in the sine diagram. We'll illustrate that in just a moment. Let us revisit an earlier example. Consider y equal to x cubed minus x, which factorizes as x times x plus 1 times x minus 1. So that y equals 0 when x equals minus 1, 0, and 1. We can draw a sine diagram for y. noting these important values of x that cause y to be 0. Then noting an alternating pattern of plus and minus symbols as you move right to left past the points that we have marked off on the x-axis. This tells us when the curve sits above and below the x-axis. To find out where the curve is increasing or decreasing, we form a sine diagram for the derivative, which in this case is 3x squared minus 1. So that y dash equals 0 when x equals plus or minus 1 over root 3. We get the sine diagram that we mentioned at the end of an earlier example. We now add our up or down notation to indicate whether the curve is increasing or decreasing according to whether the sign of the derivative is positive or negative. Now, we can be sure how the curve should undulate. In this case, up, down, and then up again as we move from left to right. What about the second derivative? Can the second derivative give us any useful information? The first derivative is 3x squared minus 1. So the second derivative, y double dash, is going to be 6x. This is 0 when x is 0. We can draw the sine diagram for y double dash, indicating that it's 0 when x equals 0. And then it has the same sign as x. Positive when x is positive, and negative when x is negative. You might remember in the last example, we used a bowl-shaped happy face symbol when the second derivative was positive. So we'll use that again here for x greater than 0. But when the second derivative is negative, we use a bowl-shaped down or sad face symbol. We now have 3 sine diagrams that gives us a fairly complete description of how the curve should behave. Where it sits above or below the x-axis, where it's increasing or decreasing, and where it's bowl-shaped up or down. The important points marked off on the sine diagram then correspond to important features of the graph. So we note them on the x-axis. Then fitting the curve to match the information about the signs of y, y dash, and y double dash. This is what we get. Of note are the points where the curve is turning around. A peak at -1 over root 3 and a trough at +1 over root 3. Then this sad face shape for negative x and this happy shape face for positive x. The point where the curve changes from sad to happy is called an inflection. the tangent line actually passes through the curve at a point of inflection. It's worth noticing and relates to something we call the second derivative test that we'll talk about later on. That the point of the curve for y equals -1 over root 3 that looks like the top of a hill correlates with the imagery suggested by the Sine diagrams for both the first and second derivatives. Similarly, for the point that the curve equals 1 over root 3, that looks like the bottom of a valley. This next example was discussed in an earlier video, and it's quite difficult. Let g be the rational function with rule x squared minus 2 divided by x minus 1, which can be rewritten as x plus 1 minus 1 over x minus 1. Here's the graph of g with vertical and oblique asymptotes. We now explore the use of Sine diagrams to gain a better understanding of the graph. First of all, g of x is 0 precisely when the numerator of the rational expression is 0, which occurs when x equals plus or minus root 2. We can form the Sine diagram for g by first noting plus or minus root 2, and that g of x is 0 at those points. We also leave room to insert the point 1, because this is the input for which the rule for g does not make sense, and we write u beneath it, an abbreviation really for undefined. Then we note an alternating pattern of signs for g of x as we move from right to left past these important points on the x-axis. Each part of the Sine diagram corresponds to some feature of the graph sitting above or below the x-axis, being 0 or being undefined. What about a Sine diagram for the derivative? As we've noted, the rho for g can be rewritten as x plus 1 minus 1 over x minus 1. The derivative is one plus 1 over x minus 1 all squared. But all parts of this expression are positive. So g dash x is positive always, provided x is not equal to 1. Now we can provide a Sine diagram for the derivative of g. We want to note that g dash of x is undefined for x equals 1 and positive everywhere to the right and to the left of 1. So we add an upward sloping symbol in each case to indicate that the function is increasing on both intervals. This behavior predicted by the sine diagram is exactly matched on the curve. But for the branch of the curve to the left, to the vertical asymptote, and to the branch to the right, note that this behavior predicted by the sine diagram is exactly matched on the curve, both for the branch of the curve to the left of the vertical asymptote and the branch to the right. There is more that we can say by considering the sine diagram for the second derivative, but we'll consider that later. So far, we have discussed sine diagrams in general for rules of functions and interpreted a positive or a negative sign for the derivative as indicating that the function is increasing or decreasing respectively. A positive sign for the second derivative indicated that the graph of the function has a bowl-shaped up or a smiley face appearance. A negative sign for the second derivative indicated that the graph has a bowl-shaped down or sad-faced appearance. Let us now discuss maxima and minima. Local and global maxima and minima, collectively called extrema for rules of functions, are related to turning points of curves. We will consider some contrasting examples and illustrate how to search for extrema by looking for the changing sign of the derivative to see where a function changes from being increasing to decreasing or from decreasing to increasing. We will finish with a discussion of the closed interval method. Consider the rule y equals f of x to be the rule of the function f. We say that f of a for some input x equals a is a local maximum if f of a is greater than or equal to f of x for all x near a. We also say that f of a is a local minimum if f of a is less than or equal to f of x for all x nearby. We may refer to either a maximum or a minimum as an extremum. And if the previous properties hold for all x in the domain of the function, then the extremum is said to be global. Just think of a global property as one that holds everywhere. To be near a on the real number line means ranging over some interval surrounding a. That interval which could be quite small, is called a neighborhood of A by mathematicians. Extrema may not exist even for the simplest of functions. For example, any linear function where the slope is non-zero increases and decreases smoothly and uniformly without bound. There's no opportunity for any value of such a function to be the greatest or the least in any neighborhood of its input. However, by contrast, any linear function with slope 0, that is a constant function, y equals k, has only one value. So that constant k becomes simultaneously both a global maximum and minimum value of the function. Consider now a function f whose rule f of x is a quadratic. The graph is a parabola, opening upwards if the coefficient of x squared is positive, or downwards if it's negative. In the upwards facing case, the apex, also called the vertex of the parabola, is the lowest point. When the parabola is situated somewhere in the xy plane and one moves across to the vertical axis, we produce a y value which is less than or equal to all y values produced by the parabola. So it becomes the global minimum. In this diagram, the apex is in the fourth quadrant, but it could be located in any quadrant. Wherever it is, when we move across to the y-axis, we always produce the global minimum. In the downward facing case, the apex now is at the highest point. So wherever the parabola is situated in the plane, when we move across to the y-axis, we produce the global maximum. So we have complete information in the two cases of quadratic functions. The apex in either case is called a turning point. In both cases, the tangent line to the curve at the apex is horizontal and has zero slope. These are special cases of a general phenomenon. A turning point for a general curve is a place where the curve changes from increasing to decreasing, or from decreasing to increasing. If any turning point has a tangent line, which is usually the case as most of the time our curves are smooth, then the slope is 0. But the slope of the tangent line is the derivative of the function. So if we want to find turning points, the natural place to look would be where the derivative is 0. Let's apply the derivative to quickly find the turning points and global minimum of this particular quadratic. To solve this, observe that the derivative is 2x minus 2, which is 0 when x equals 1. So the turning point must occur when x equals 1, in which case y equals minus 2. So the turning point has coordinates 1, minus 2. And the global minimum is the y coordinate, which is minus 2. All of this is confirmed by drawing the associated parabola. Notice, if we draw the Sine diagram for the derivative, we see that the derivative is negative to the left of x equals 1 and positive to the right, confirming that the function is decreasing from the left and increasing to the right of the apex. The next example involves a cubic polynomial. And the problem is to find all local and global extrema. Firstly, over the whole real line, and secondly, over the restricted interval between 0 and 5. To solve the first part of the problem, we find the derivative, which is a quadratic, and which turns out to factorize as 3 times x minus 1 times x minus 3. So that the derivative is 0 when x equals 1 and 3. Very quickly, we've narrowed down the possibilities for extrema to just these two inputs. By drawing the Sine diagram for the derivative, we should be able to tell what kind of extrema occur and where. We see from the factorization of y dash or y, the first derivative, that if x is bigger than 3 or less than 1, then y dash is positive. And if x is between 1 and 3, then y dash is negative. So we get an up, down, up pattern of behavior of the curve with turning points at x equals 1, where there is a local maximum, and x equals 3, where there is a local minimum. The local maximum is the value of the function at x equals 1, which is 5. And the local minimum is the value at x equals 3, which is 1. Neither of these local extrema can be global, because with non-restricted domain, the cubic can take arbitrarily large positive and negative values. Here's the graph of the function with its turning points and the local extrema appearing on the y-axis. In the second part of this problem, we need to find all extremum when the domain is now restricted to the interval from 0 to 5. The local maximum and minimum from the previous calculation are important because inputs x equals 1 and 3 fall within this domain. The question is really how far the curve falls away to the left and how much it climbs to the right. So we evaluate the function at the left-hand endpoint of the interval x equals 0 and get the value 1, and at the right-hand endpoint x equals 5 and get the value 21. We can now compare the full values 5, 1, 1, and 21. The global maximum is just the largest of these, which is 21. And the global minimum is the smallest, which is 1. This solves the second part of our problem. The graph is actually quite steep at x equals 5. So to see what's going on, we need to adjust the scale of the axis, and then you can see how easily the local maximum of 5 is surpassed by the global maximum of 21. The global minimum, in fact, is achieved exactly twice, both at the left-hand end of the interval and at x equals 3 inside the interval. The technique that we just used applies generally to curves and is called the closed interval method. Consider a continuous function f. To find the inputs between a and b, including a and b. The interval a, b of inputs with squared brackets is referred to as closed because it contains both of the endpoints. Being continuous, you can imagine drawing the graph of f without lifting your pen off the paper. To find the global maximum and minimum values, it suffices to find the largest and smallest values of the function. When evaluated at the endpoints of the interval a and b, and the inputs where the derivative turns out to be 0, or where the derivative is undefined. In the last example, the derivative was defined everywhere. This is a very powerful result because for most functions, there are an infinite number of possible inputs. And this is to say that you only have to restrict attention typically to just a finite handful of points. In the last example, which is quite a sophisticated cubic, we only needed to evaluate the function at 4 points. Let's finish with an example where the derivative is not defined everywhere. The function f has the rule f of x equals the magnitude of x minus 1 plus 3, restricted to x between minus 2 and 5. If x is greater than or equal to 1, then the magnitude sign can simply disappear, and the rule quickly becomes x plus 2. If x is less than 1, then the magnitude sign can be removed by placing x minus 1 by 1 minus x. And the rule quickly becomes 4 minus x. These are two linear pieces with derivative 1 for x greater than 1 and minus 1 for x less than 1. Note that the values 1 and minus 1 are both non-zero. In fact, there can be no derivative at x equals 1 because it's a sharp point on the curve. So the tangent line becomes ambiguous and there is no well-defined slope. Here's the graph trimmed to only include inputs x between -2 and 5. We can solve the problem completely by inspecting the graph. But let's see what the closed interval method predicts. The method tells us we only need to check endpoints at x equals 1, since the derivative is never 0 and is undefined at x equals 1. So we check f of -2, which equals to 6, f of 5, which evaluates to 7, and f of 1, which evaluates to 3, of which 7 is the largest and 3 is the smallest. This corresponds on the graph to the global maximum and global minimum of the function, respectively. Note that the value 6, which occurs at the left-hand endpoint of the domain, is a local but not global maximum. This then solves our problem. Note that though we looked at the graph, the closed interval method can be followed blindly and mechanically without any visual assistance. It's important to have such methods to deal with functions whose graphs are so complicated that it may be too difficult to draw them or imagine what they look like. In this portion of the video, we discussed local and global maxima and minima, collectively called extrema for rules of functions, and considered associated turning points, where the curve changes from increasing to decreasing or decreasing to increasing, and found them by exploiting the derivative and the fact that the tangent line to a curve at a turning point must be horizontal and have 0 slope. We finished with a discussion and illustration of the closed interval method, which locates global extrema by narrowing attention to endpoints of the domain and where the derivative is 0 or undefined. Now, let us formally discuss concavity. Concavity is a property of curves where the slopes of tangent lines are either increasing or decreasing, leading to notions of concave up and concave down, and points of inflection where concavity changes either from concave up to down or from concave down to up, which will also point to the property that the tangent line pass through the curve. Let us begin by discussing concavity. Think of the property concave up of a curve as corresponding to the curve being in a bowl-shaped up configuration. If you look at miniature tangent lines to the curve as you pass from left to right, you'll notice that the slopes change from being very steep and negative to shallow and negative to being zero as you move through the turning point, to being shallow and positive, to being steep and positive. The slopes of the tangent lines are increasing. This corresponds to the derivative of the rule of the original function being itself an increasing function. So its derivative, the second derivative of the original function, denoted by y double dash, should be positive. Now consider the opposite property, concave down, which corresponds to the curve being in a bowl-shaped down configuration. Now, if you look at miniature tangent lines to the curve, as you pass from left to right, you'll notice that the slopes change from being steep and positive to shallow and positive, to being zero as you move through the turning points, to being shallow and negative, to being steep and negative. The slopes of the tangent lines are decreasing. This corresponds to the derivative of the rule of the original function being itself a decreasing function. So the second derivative of the original function y double dash should be negative. A point of inflection, or we may simply say an inflection, is a point where the concavity changes from being concave up to being concave down, or from concave down to concave up. We can picture the first case in a couple of ways. Transitioning from bowl-shaped up to bowl-shaped down, and the moments of transition are called inflection. You can watch the way miniature tangent lines to the curve behave as you pass from left to right for the first curve displayed here and for the second curve. You might notice that the tangent line crosses the curve at the point of inflection. The slope of the tangent line, which is the derivative denoted by y dash, reaches a maximum at that moment of transition at the inflection point. So its derivative denoted by y double dash must become zero. In summary, for the case where concavity changes from concave up to down, the derivative reaches a maximum and the second derivative is zero. Consider the second type of transition from concave down to concave up. We can picture that in a couple of ways, transitioning from bowl-shaped down to bowl-shaped up. Note the moments of transition, the inflection. Now watch the way the miniature tangent lines behave as you pass from left to right. For the first curve and for the second curve, and again, the tangent line crosses the curve at the point of inflection. This time, the derivative y dash reaches a minimum at that point of transition at the inflection. And again, the second derivative, y double dash, must become 0. In summary, for the case where concavity changes from concave down to up, the derivative reaches a minimum and the second derivative is 0. So we've considered variations in the way concavity can change and the effects they have on the derivative and second derivative. The upshot of this is that changes in concavity can be detected by looking at changes in the sign of the second derivative. And all of this information will be captured in its Sine diagram. To see how this works, let's sketch the curve y equals 9x minus x cubed. Let's first factorize. This will be useful in just a moment for detecting x-intercepts. The first derivative equals 9 minus 3x squared, which again can be factorized to give us what we see here. The second derivative is just minus 6x. Putting these together, we can start to build Sine diagrams, and we'll do this for the first and second derivatives. In the case of the first derivative, we say that the important inputs for x are plus and minus √3, where the derivative is 0. And we get a pattern of signs, minus, plus, minus, as we move from left to right. So the curve is decreasing, then increasing, then decreasing again. In the case of the second derivative, the important input for x is 0, where the second derivative is also 0. And the pattern of signs is plus, minus, as we move from left to right. So the curve must be concave up to the left of 0, indicated by the smiley face symbol, and concave down to the right of 0, indicated by the sad face symbol. All of this information is noted here to the side, as we can list the main features of the curve. The y-intercept is just 0. The x-intercepts will be 0, 3, and minus 3. From the Sine diagram for the derivative, there is a local minimum occurring for x equal to minus √3, and a local maximum when x equals plus √3, fitting a curve. Now we can sketch the curve with confidence. Here are the important points on the x-axis. And we're fitting a curve which is concave up to the left of 0, concave down to the right with a local minimum at x equal to -√3 and a local maximum at x equal to +√3. The local maximum and minimum values you can quickly work out from the rule for the function, and they become plus or minus 6 times the square root of 3. And the origin is the point of inflection where the concavity changes. This completes the sketch of the curve y equals 9x minus x cubed. Let us now discuss the sketching of a cusp. Let us consider the function y equal x to the 2/3. Finding the first derivative, we get 2/3 x to the minus 1/3. The sign diagram for the derivative involves one important point for x, namely x equal to 0, where the derivative is not defined. The pattern of signs is simply negative, positive, as the sign of the first derivative agrees with the sign of x. So the curve is decreasing to the left of 0 and increasing to the right. This means that there is a global minimum at x equals 0. Noting that the curve is continuous even though the derivative is undefined at x equals 0. We can say more about the behavior of the derivative near the origin using limit notation. The limit of y dash x, the limit of the first derivative as x approaches 0 from below is a limit of 2 divided by 3 times the cube root of x, which becomes arbitrarily large and negative. And we use the minus infinity notation to capture this. On the other hand, the limit of the first derivative as x approaches 0 from above becomes plus infinity, capturing the idea that the derivative gets arbitrarily large and positive. These two limits summarize the behavior of the slopes and imply that the tangent lines themselves become more and more vertical as you approach 0 from either side of it. Let's continue differentiating. The second derivative becomes 2/3 of minus 1/3 times x to the minus 4/3. Using the differentiation rule. Now, we're emphasizing the square in the denominator, as this tells us that it's always positive. So the entire fraction is always negative, provided x is not equal to 0. We can now build the sine diagram for the second derivative, which again has 0 for an important point for x, and y double dash, or the second derivative, is undefined. Now, the pattern of sine is negative, negative. So we have concave down in both cases. In summary, we have the derivative and the second derivative and their respective signs, and the contrasting unbounded behaviors of the derivative as x approaches 0 from each side. We can now draw the graph that matches all of this information, producing a continuous curve with a sharp point, a cusp at the origin, which also coincides with the global minimum value y equals 0. This completes the sketch of the curve. In this section of the video, we discuss notions of concavity of a curve, including the properties of being concave up and concave down, and points of inflection where concavity changes either from concave up to down or from concave down to up. We illustrated the ideas by working through a couple of contrasting examples, including a cusp, and exploited information provided by the sine diagrams of the first and second derivatives. Now, let us bring together the whole range of ideas and techniques that we have been discussing so far in this video to sketch a curve in the plane. Of central importance are the sine diagram for the derivative, which tells us where the curve is increasing or decreasing. And we'll also look at the sine diagram for the second derivative, which tells us where the curve is concave up or down. We begin by making some general remarks about curve sketching, by which we mean more specifically sketching or drawing the graph of the function y equal fx in the xy plane. The scales of the x and y axes don't need to be the same, and the axes are positioned on the page depending on where the important features of the graph will appear. Always aim for simplicity and clarity, and focus on the main qualitative features. Extra details such as coordinates of points can be added depending on the requirements of any particular problem. It's a fairly natural list of features to look for. First, look for the y-intercept, where the curve crosses the vertical axis. In the case that x equals 0 is in the domain of the function, which is simply found by evaluating f0. And then look for the x-intercepts, where the curve crosses the horizontal axis. But this might be difficult since it involves the solution of the equation fx equals 0. Indeed, A given problem might be to attempt to solve the equation fx equals 0, typically by using some approximation method from advanced calculus. And the main purpose of the sketch of the curve may be just to get started with the final aim of knowing roughly where the x-intercepts might be. After we have figured out the x and y-intercepts, we want to look for asymptotic behavior, which roughly speaking means seeing what happens when things get large, such as when x gets arbitrarily large and positive or arbitrarily large and negative, leading to possible horizontal or oblique asymptotes, or whether there are any vertical asymptotes near which y can get arbitrarily large and positive or negative. Then we look for where the curve might be increasing, where the derivative could be positive or decreasing, where the derivative could be negative, which will help us find turning points, where the derivative might be 0, and these could be local or global maxima or minimum. This information typically is stored in the Sine diagram for the derivative. Then we look for where the curve might be concave up, where the second derivative might be positive, or concave down, where the second derivative might be negative, which helps us find possible points of inflection, where the second derivative might be 0. This information typically is stored in the Sine diagram for the second derivative. Let's work through this list to sketch the following cubic curve. The y-intercept is -1. The x-intercepts look tricky, and we can say more about that later and roughly where they might exist. In fact, there is only one x-intercept in this case, but that's not obvious from the rule itself. Let's now consider asymptotic behavior. As x gets large and positive, the cubic is dominated by the leading term 2x cubed, and also gets arbitrarily large and positive, indicated by the use of the infinity symbol. As x gets large and negative now, the cubic also gets arbitrarily large and negative, indicated by the use of the negative infinity symbol. There are certainly no horizontal asymptotes, nor are there any oblique asymptotes. Though it's not obvious why there are none, some careful reasoning is given in the notes. The derivative of this function is this quadratic, which quickly factorizes. And we can see it's 0 when x equals 1 or 2. And then build a Sine diagram with this pattern, plus, minus, plus, corresponding to increasing, decreasing, increasing, with a maximum occurring at x equals 1 and a minimum at x equals 2, with y values 4 and 3 respectively, giving a turning point 1, 4, with local maximum 4, and another turning point 2, 3, with local minimum 3. We get the second derivative by taking the derivative of the first derivative, and we get 12x minus 18, which factorizes as 6 times 2x minus 3. So this equals 0 when x equals 3 over 2. And we can build its sign diagram with a pattern of negative, positive. So concave down followed by concave up, with changing concavity and inflection when x equals 3 over 2. We can evaluate y for this input yielding 7 over 2. So the point of inflection has coordinates 3 over 2, 7 over 2. We can now put all of this information together, noting important points on the axes and the position of the y-intercept, the two extrema and the inflection, and then drawing a smooth curve that passes through these points, consistent with the information of the sign diagrams. This completes the sketch of the cubic. Note that the sketch indicates that the curve crosses the x-axis somewhere between 0 and 1. And there is only a single point where it crosses the x-axis. So let's sketch the graph of the function gx equals x squared minus 2 over x minus 1. Let's go through the checklist systematically. First, the y-intercept is 2. This is the result of evaluating the rule when x equals 0. The x-intercepts turns out to be straightforward. It's simply when the numerator x squared minus 2 is 0, which occurs when x is plus or minus the square root of 2. The asymptotic behavior is interesting. The limit as x approaches 1 from above of gx is minus infinity, which means gx gets arbitrarily large and negative. And the limit as x approaches 1 from below becomes positive infinity, which means gx gets arbitrarily large and positive. And x equal 1 is a vertical asymptote. The interesting asymptotic behavior occurs as x gets large and positive, or large and negative. By rewriting the rule for g as x plus 1 minus 1 over x minus 1, gx is approximately x plus 1 for large positive or negative x. So that the line y equals x plus 1 becomes an oblique asymptote. The derivative of gx is 1 plus 1 over x minus 1 squared. And this is positive for all x not equal to 1. The Sine diagram will then be plus plus on either side of x equals 1, where the first derivative is undefined. So the curve is increasing for x less than 1 and increasing again for x greater than 1, so that there are no turning points. We can rewrite the derivative as 1 plus x minus 2 to the negative 2. So the second derivative becomes 0 plus 2 times x minus 1 to the negative 3. The second derivative then becomes negative 2 divided by x minus 1 cubed. And its sign, positive or negative, must be the opposite of the sign of x minus 1. This produces the following Sine diagram, with the second derivative being undefined at x equals 1. And the pattern is plus followed by minus, so that the curve is concave up for x less than 1, followed by concave down for x greater than 1. Now, we can gather all of this information and set up the axes for the sketch of the curve, noting the important points 2 on the y-axis and plus and minus root 2 on the x-axis, and the oblique and vertical asymptotes. We can now draw this curve with the 2 branches that is consistent with all of this information. The feature that we didn't discuss previously was concavity. And we see the concave up branch to the left of the vertical asymptote and the concave down branch to the right. Notice that these are not full smiley or sad faces, so to speak. The slope is increasing in the left-hand branch of the graph and decreasing in the right-hand branch, which is consistent with the pattern of plus and minus in the Sine diagram for the second derivative. The reason for the oblique asymptote is that the rule for the function splits up into a linear piece, x plus 1, take away this extra piece, 1 over x minus 1. This means that to the right, the curve is approaching the oblique asymptote from below, because we are taking a small positive piece away from the linear piece. But to the left, the curve is approaching the oblique asymptote from above, because we are taking away a small negative piece, which is the same as adding a small positive piece. It's interesting to ask, what happens if we add 1 over x minus 1 in the rule for the function instead of taking it away. So let's work through the checklist for sketching the curve with this variation. X plus 1 plus 1 over x minus 1. Let's work through the checklist for sketching the curve with this variation. After a bit of algebraic manipulation, the rule becomes x squared over x minus 1. The y-intercept now is 0. And we quickly see there's exactly one x-intercept, which is also 0. As in the previous example, x equal 1 becomes the vertical asymptote. But notice that the behavior is different. The limit as x approaches 1 from above now turns out to be plus instead of minus infinity. And the limit as x approaches 1 from below now turns out to be minus instead of plus infinity. The oblique asymptote again is the line y equals x plus 1. The first derivative now becomes 1 minus 1 over x minus 1 squared. Which simplifies to x squared minus 2x over x minus 1 all squared. Which can further be factorized to be x into x minus 2 over x minus 1 all squared. Notice that the first derivative is undefined at x equals 1. We can now build a Sine diagram for the first derivative, which produces the pattern of signs plus, minus, minus, plus as we move from left to right past the important points for x, producing the pattern increasing, decreasing, decreasing again, and increasing, with a maximum at x equals 0 and a minimum at x equals 2. Evaluating f at x equals 0 and 2 produces a turning point 0, 0, the origin in fact, with local maximum of 0 and 2, 4 with a local minimum of 4. To find the second derivative, first notice that, now let's find the second derivative. We can rewrite the first derivative as 1 minus x minus 1 to the negative 2. And this gives us the second derivative as 2 times x minus 1 to the negative 3 power. Which can be rewritten as 2 over x minus 1 cubed. So this helps us to see that the second derivative is undefined at x equal 1. And otherwise, it's non-zero, in which case it's clear that the sign of the second derivative is the same as the sign of x minus 1. So we can quickly So we can quickly build a sine diagram with the pattern minus, plus, sad face, followed by smiley face. So that the curve is concave down for x less than 1 and concave up for x greater than 1. Putting this information together, drawing the axes and the asymptotes and so on, we get the curve in two branches. Where the first branch, concave down, achieving a local maximum corresponding to the origin, and the second branch, concave up, achieving a local minimum corresponding to the point 24. Notice how, by contrast with the previous example, the curve gets closer and closer to the oblique asymptote from above as we move to the right, and from below as we move to the left. In this section of the video, we produce a checklist for sketching curves in the plane and work through the details in 3 contrasting examples. The first involve a cubic function where there are no asymptotes, but there were 2 turning points and an inflection. Interestingly, the sketch shows that there is exactly 1 x-intercept, and in this case, roughly where to find it, which will be useful if we wanted to go further and solve an associated cubic equation. Second and third examples involve rational functions with similar rules but contrasting behavior. Both of them have 2 branches, an identical vertical and oblique asymptote, but approached differently. One curve had no turning points, while the other had 2. They both had shifts in concavity as one passes across the vertical asymptote, so to speak, which we may think of as creating some kind of inflection of plus and minus infinity. In this video, we brought together a range of ideas and techniques that led to an ordered and systematic approach to sketching a curve in the xy plane. Of central importance are the sine diagrams for the first and second derivatives. The sine diagram of the first derivative tells us where the curve is increasing or decreasing, and where turning points or local maxima or minima occur. While the sine diagram for the second derivative tells us where the curve is concave up or down or inflected. You should now be in a position to sketch the graph of most functions now. Thank you very much for watching, and I look forward to seeing you again soon.